In Part 5 of the Unit 4 notes, we are going to be looking at quantum numbers. Schrodinger's wave function predicts a 3D region around the nucleus called an atomic orbital, which describes the electron's probable location. An atomic orbital is like a fuzzy cloud in which the density corresponds to the likelihood of finding an electron. 4 quantum numbers can be used in order to describe information about the orbitals, including the energy level, the shape, the orientation, and the electrons within them, specifically their spin. Our first quantum number is called the principal quantum number. This number indicates the main energy level occupied by an electron, and it is symbolized by the letter n. The value of n must be a positive integer, such as 1, 2, or 3. The higher the value of n, the further the atomic orbital is from the nucleus. This is the same type of designation that we also saw within the Bohr model. So you can see within our diagram, our electrons which are closest to the nucleus are going to be designated within n equals 1, and as you get further away, that number will increase. The angular momentum quantum number indicates the shape or sublevel of the orbital an electron occupies, and it is symbolized by a script L. The values of L are all positive integers from n-1 counting down to 0. Each number corresponds with a specific shape. So for example, if I were given n equals 2, so I'm at the second principal energy level. In order to find the values of L which are allowed at that level, all I need to do is subtract 1, so 2 minus 1 is 1, and then I count down to 0, which in this case is just 0. So I end up with L values of 1 and 0. These L values correspond with letter designations for the shapes. So what this means is at the second energy level, I can have an s orbital, which is 0, and a p orbital, which is 1. You can see examples of s and p orbitals over here. So an s orbital looks a lot like a sphere, and a p orbital looks like a dumbbell type of shape. The angular momentum quantum number is also sometimes referred to as the orbital quantum number. For our first checkpoint question, we are going to determine the shapes which are present at n equals 2. So if I had n equals 2, that means for L, I could have 1 and then 0. Again, I am just subtracting 1 and then counting down to 0. These two numbers correspond with specific shapes. The 0 corresponds with the s orbital, the 1 corresponds with the p. So I could have an s and a p orbital when I am at the second energy level. For the shapes, an s orbital is a sphere, and the p orbital is the dumbbell shape. It looks kind of like a figure 8. Our third quantum number is the magnetic quantum number. This describes the orbital orientation in space around the nucleus along the x, y, and z axis, and is symbolized by m or m sub L. The values of m sub L are whole numbers, including 0, from negative L to positive L. The number of values indicates the number of orientations present, or the number of directions in which the orbitals would be pointing in. Here you can see 3 p orbitals which are each pointed along a different axis. So this one happens to be along the x-axis, this one is along the y, and this one is along the z. Determine which shapes and how many orientations will be present at n equals 2. For n equals 2, we already determined from the previous checkpoint question that L was equal to 1 and 0, which corresponded to s and p orbitals. But now we also want to know how many orientations are available for those p orbitals, the highest energy orbital that is here. In order to do that, I am going to take all of the positive and negative versions of these numbers, which in this case is not many. I could have a negative 1, a 0, there's no negative version of 0, and then a positive 1. So that tells me that 3 orientations are possible. And for those p orbitals, those orientations are going to correspond with directly along the x, y, and z axis. This slide has a picture that is going to show you the different types of orbitals which are possible as we progress through energy levels. We have an s orbital, which is our sphere, the p orbitals, which are the dumbbell shapes, which can be along the x, y, or z axis. Now here I have 3 of these p orbitals, one along the x, one along the y, one along the z, and you can see here how that would all fit together. So they can all kind of occupy the same space here, fitting within the different directions. So those are where the electrons will be located. Next up, we have the d orbitals. The d orbitals are referred to as a double dumbbell, so it looks kind of like a double figure 8. So you can have these along 5 different orientations. And if all 5 of these orbitals were fit together, they would look like this. Finally, the most complicated are the f orbitals, which you can see in our diagram here going across. This chart shows what energy levels are possible, what shapes and orientations are possible at each of our energy levels. So we know that if we had n equals 1, subtract 1 from that, you would end up with 0, so you are only able to have a 1s orbital. At the second energy level, when you subtract, you end up with 0 and 1, so you end up with 2 possible shapes, which correspond to s and p. At n equals 3, you have 3 possible shapes, so you can have s, p, and d orbitals. And at n equals 4, you can have 4 possible shapes, s, p, d, and then finally f. Our final quantum number is the spin quantum number. This number describes the spin for a given electron. An electron can have one of 2 possible spins, a positive 1/2 or a negative 1/2. We typically represent these spins as an arrow going either up or down. A single orbital can hold a maximum of 2 electrons, and each electron must have a different spin. Here we have a picture which is going to show how all of these orbitals will eventually fit together. So at the very center here, our one that is closest to the nucleus, we have a 1s orbital. So 1 because it is closest to the nucleus, s because it is a sphere. And the s orbital only has one orientation, so we just have the one sphere here. When we get out a little bit further, we have the second energy level, which also has an s orbital. So we have our secondary sphere right here. But at the second energy level, there are also p orbitals which are possible, which have 3 total orientations. So I can see p orbitals right here going along the x, y, and z axis. So all 3 of the orientations are represented by the pink p orbitals that are shown right here. If I were to go even further out, then I would end up at the third principal energy level, where I end up with another sphere. So this is often compared to the nesting dolls that you might be familiar with, where one doll fits inside of another, and so on. So that's essentially what is going on here with these orbitals. Remember, these orbitals are not solid spaces that could potentially actually interact with one another in that type of way. They are able to occupy the same space, since they are just probable locations for electrons. For our next checkpoint question, we are going to start by trying to use one word to describe each of the 4 quantum numbers that we have covered so far. And this will help us as we're trying to remember what each of them allows us to do. Our principal quantum number could be summarized by the word energy. Another good word that could be used to describe that might be distance, since we're referring to the energy level or the distance from the nucleus. The angular momentum quantum number could be summarized by the word shape, since this tells us whether we have s, p, d, or f orbitals at each energy level. The magnetic quantum number could be summarized by the word orientation or direction. This quantum number tells you which direction your orbitals are pointed in. And finally, the spin quantum number tells you the spin. So whether your electron is spinning up or spinning down. For our next question, we're given n equals 3, and we are trying to find the values of both L and M. In order to find L, we take the value of n and we subtract 1. So that would be 2. And then we count down to 0. So if I'm at the third energy level, that corresponds to 2, 1, and then 0. So 3 potential shapes, which are S, P, and then D. For M, or M sub L, I need to take all of the positive and negative versions of these numbers. That would be a -2, a -1, 0, and then 1 and 2. The fact that there are 5 numbers here tells me that there are 5 orientations, or 5 directions that the highest energy orbitals can point in. Highest energy orbital being the d orbitals. So my s orbital will only have 1 orientation, p will have 3, and d orbitals will have 5 orientations. So for question 3 here, we already kind of answered that. What shapes are possible? We have our S, P, and D shapes, and for the orientations, we have 5 potential orientations for our d orbitals. That concludes part 5 of the Unit 4 notes. When we come back for part 6, we will be making orbital notation diagrams.